in the last analog to digital converter, one of the standard analog to digital converter is dual slope analog to digital converter. In this dual slope analog to digital converter, we are looking a integrator circuit. This operational amplifier, we are having the usage of the integrator here. Whenever we are having the usage of op-amp as a integrator, we will be looking the integrator output or the output of this circuit. Basically, if the input is VI, VO we are going to read as minus of 1 by RC integration 0 to T VI dt. So it is the output what we are going to read for this input VI. And of course, this RC we can look as tau. So minus 1 by tau 0 to T VI dt. So if at all the VI is a time varying signal, the VI is a square wave, then we are going to look a ramp signal, or we are going to look a triangular wave, you can say. We are going to look a triangular wave as the output for a square wave, and so on. So basically the circuit is integrating the input signal. So such circuit we are having usage here as a integrator, and this is comparator, and we are looking here for this comparator. The reference voltage is ground potential 0 volt, and the reference voltage is connected to the non-inverting terminal. In our earlier three circuits, the reference voltage was at the inverting terminal, and whereas here the reference voltage is at the non-inverting terminal, that too the reference voltage is 0 volts. This comparator output is coming as one of the input of this 2 input AND gate. 2 input AND gate, the second input is the clock signal. So that as long as this comparator output is 1, as long as the comparator output is 1, a clock is allowed to pass. So this binary up counter, as similar to the counter type analog to digital converter, this binary up counter value is going to get increment. But as and when the comparator output is 0, a clock is not having chance to pass through this AND gate. So the principle is very similar to the counter type analog to digital converter as far as the clock is concerned to this binary up counter. And we are looking here, it is a T flip-flop. T flip-flop, T input is permanently connected to 1. And for this T flip-flop, the clock is coming from the MSB bit of this binary up counter. It is having a positive edge triggered, so that whenever MSB bit is changing 1 to 0, it is going to be the clock to this T flip-flop. Whenever T flip-flop is getting a clock, the T flip-flop is going to get toggle. It means if the switch is at VA, it is coming to at minus VR. If at all the switch is at minus VR, it is switching to VA as and when there is effective clock signal. And there is effective clock signal if and only whenever MSB bit is changing 1 to 0. If at all MSB bit is changing 0 to 1, or MSB bit is changing 1 to 1, or MSB bit is changing 0 to 0, these transitions are not giving any clock effect to the T flip-flop. The clock effect we are looking to the T flip-flop if and only B and minus when it's changing 1 to 0. So these are the various blocks what we are looking in this dual slope analog to digital converter. Based on this description, we can look here. The dual slope ADC is having one block is integrator circuit, one block is comparator, next is binary up counter, the last one is switch control circuit. So it is the integrator, it is the comparator, it is a binary up counter, it is the switch control circuit. These are the 4 blocks we are having in this dual slope analog to digital converter. Now let's look to the operation of this dual slope analog to digital converter. The switch will be connected to the analog signal VA. So initially the switch will be connected to VA, that is the signal which is to be converted to the digital form. So the digital readout we are going to read from this binary up counter outputs. So whenever VA is the input to this integrator circuit, the integrator circuit output VO will be minus of 1 by tau integration 0 to t VA dt. So it is nothing but minus of VA by tau into t, where tau we already mentioned, it is time constant RC. For this integrator output, if you draw the waveform, so it is in the form of y is equal to mx form, so that it is a line which is passing through the origin with a slope of minus VA by tau. Because of the negative slope, the line is in the fourth coordinate. So it's the line for this equation 1. As long as integrator output we are looking below this 0, below this x-axis, below this time axis, as long as the integrator output is negative, in other way, the comparator output will be 1. So if you give the waveform to the comparator output, comparator output we named as a VC, VC will be 1, As long as VC is 1, clock pulses are allowed to pass. So initially here also all the bits of the comparator will be set to 0. Whenever all the bits are set to 0, because of the comparator output is 1, clock is getting a chance to pass. So once the clock is entering, we are looking, the counter value will be incremented to 1 for every clock pulse. So the counter is going to get increment like this. Suppose we are looking to a 3-bit case, it is going to get the clock pulses like this. So that counter values go on getting increment. And in this example, MSB bit is B2. And B2 value we are looking, it is changing either maybe 0 to 0 or maybe 0 to 1 or 1 to 1. As long as the change is 0 to 0 or 0 to 1 or 1 to 1, it is not effective clock to the T flip-flop. As long as it is not effective clock to the T flip-flop, the T flip-flop is not going to toggle. So that as long as the integrator output is below this x-axis, we are looking, comparator output is 1. Hence clock pulses are go on allowed to pass. Even until to this 7th clock pulse, we are looking for this 3-bit case. The MSB bit, that is a B2, is not having a chance to change from 1 to 0. Even until to the 7th clock pulse, we are having the change on the MSB bit B2, either maybe 0 to 0 or maybe 0 to 1 or 1 to 1. Hence, the T flip-flop was not able to get a toggling till now. After the 7th clock pulse, this 3-bit case we are talking, as and when the next clock pulse is coming, whenever the next clock pulse is coming, all the bits are coming to 0. So we are looking at this time, the MSB bit B2 is changing from 1 to 0. So it is the effective clock to the T flip-flop. Because of this 1 to 0, the T flip-flop is going to get toggle. Whenever the T flip-flop is going to get the toggle, the switch is changing from VA to minus VR. The switch is changing from VA to minus VR. So switch is changing from VA to minus VR. In fact, it is happening, consider at T is equal to T1, where T1 is, for 3-bit case, 8 clock pulses, for n-bit case, to the power of n number of clock pulses. Whenever n is 3, it is 8. For n-bit case, to the power of n number of clock pulses. So that to the power of n into Tc, where Tc we are considering in all our discussion, this is the clock repetition time. So it is happening at T1, where T1 is to the power of n into Tc. Now for T greater than or equal to T1, for T greater than or equal to T1, if at all we want to look to the integrator output, for T greater than or equal to T1, if you want to look to the integrator output, the integrator output we are having as minus VA by tau into T1 plus VR by tau into T minus T1. It is the equation we are having possibility to read from the integrator output. It is nothing but in the form of the coordinate geometry knowledge we can speak as it is nothing but equal to y is equal to mx plus c, where c is the initial value. Initial value is minus VA by tau into T1. At a t equal to T1, initial value we are looking as minus VA by tau into T1. And for t greater than or equal to T1, it must be slope of minus VR by tau. It's a plus VR by tau, T minus T1. So for this portion, if at all we are looking, the integrator output is switching from this negative slope to positive slope. It is switching from this negative slope to positive slope. So that integrator output will be moving towards the time axis, but still it is below this 0. It is below this time axis, below this x-axis. As long as it is below this x-axis, we are going to look to the comparator output is 1. Once the comparator output is 1, the clock pulses are allowed to pass. The clock pulses are allowed to pass. It means after completing this full length, now the counter output is going to start again with increment. As and when the clock is coming, it is going on getting increment. And so on, and so on. So this positive slope line, as long as below this time axis, below this reference voltage 0, the clock pulses are allowed to pass, so that counter values go on getting increment. But we know this positive slope line will cross this time axis, that is t axis or x axis at one or other time. As and when it is crossing the x axis at time axis, the comparator output is falling to 0. As and when the integrator output is getting positive value, once it is crossing this time axis means it is getting a positive value. Once it is getting a positive value, the comparator output is coming to 0. So that now there is no chance of clock pulses entering into this binary up counter. Once the clock pulses are not having chance to enter into the binary up counter, there is no further change in the binary up counter value. It is going to be the stable readout. So this stable readout we are going to read as a digital output for this input analog signal. So basically what we are looking is the number of clock pulses which are entering in the duration from T1 to T2, the number of clock pulses which are entering in the duration from T1 to T2 to this counter, that is going to be the equivalent digital output for this input analog signal. So if the number of clock pulses entered in the duration, if you name say m, we need to prove m must be proportional to the input analog signal. At all, M is proportional to input analog signal, then it is possible to accept the circuit is converting analog data to digital form. So let us verify. At T is equal to T2, from this equation 3 if you look, VO must be 0, VO must be 0. So while substituting these values in this equation 3, we are looking at it is 0, it is minus VA by tau into T1 plus VR by tau T2 minus T1. So this will be cancelled. The number of clock pulses entered in the duration T2 to T1, if you name as M we are going to look the number of clock pulses entered in the duration from T1 to T2, if you name as M will be, if at all we are looking here, it is coming to be VA by VR into T1, where T1 is by using equation 2 to the power of N into Tc. So that it is coming to be to the power of N into Tc by VR VA, where M is number of clock pulses entered in the duration in the time interval from T1 to T2, from T1 to T2, where M is the number of clock pulses entered in the time interval from T1 to T2. So the number of clock pulses entered in the time interval T1 to T2 is M, and we are able to look here to the power of N is a constant for a given analog to digital converter based on the size. If it is 3-bit, it becomes 8. The 4-bit, it becomes 16, so on. So to the power of N is a constant, and Tc, what is the clock we are using, the clock time period is a constant, and the battery reference voltage what we are using, it is also constant. This total thing is a constant, so that we are able to look here M is proportional to VA. Hence, what is the readout we are looking here from this counter output, that becomes the equivalent digital output for the input analog signal. So we are looking here, the principle is very straightforward principle. Whenever this integrator input is connected to the analog signal VA, we are going to look, the capacitor is basically going to charge. The capacitor is going to charge, and the charging voltage is proportional to the input analog signal. Charging voltage is proportional to the input analog signal. That's the reason why we are looking VO, charging voltage. That is the voltage we are going to read as output from this integrator, is proportional to the input analog signal. So based on this, the counter is going to affect, and whenever the counter is incrementing, it is getting a chance it is getting a chance for every clock pulse, because of the comparator output is 1. For every clock pulse, binary counter is getting a chance to get increment. So until it is not coming to 0, 0, 0, the change on the MSB bit will be either maybe 0 to 0 or 1 to 1, 0 to 1. These are not coming as effective clock to the T flip-flop, so that T flip-flop was not able to toggle until to 0, 0, 0. As and when it is getting 0, 0, 0, we are looking 3-bit case. The MSB is changing 1 to 0, so T flip-flop is going to get toggle. Whenever it is getting a toggle, switch is moving from VA to minus VR. Whenever it is moving from VA to minus VR, the integrator is getting now positive slope. So because of positive slope, we are going to look, the waveform is moving towards the first coordinate. And during this interval also, we are looking, the comparator output is 1, so the clock pulses go on entering. So how many number of clock pulses are captured in the interval from T1 to T2 until it is not crossing to this x-axis? That number we are going to read as the digital output, that is proportional to the input analog signal. So the conversion principle is very straightforward principle, and circuit is simple circuit. This analog to digital converter may be of any size. The hardware is concerned, only this is the hardware. They are not having increasing in the number of comparators or anything else. Only up counter size is to be increased. So conversion principle is straightforward principle, and the circuit complexity is less. These are generally considered to be the advantages of this dual slope analog to digital converter. And we are naming it is dual slope. The reason is, for one part of the integrated output the slope is negative, and other part of the integrated output is by using equation 3. So we can look for other part of the integrated output the slope is positive. So we are looking the integrated output, one part is a negative slope, other part is a positive slope. It is a reason to name it is a dual slope ADC. So based on this, of course, it is named as dual slope ADC. And now you can see why we named earlier circuit of counter type as single slope. So there it was only one slope, whereas here we are looking positive slope and negative slope. So to distinguish counter type from this, we named that circuit as a single slope. So this dual slope, it is also named as integrated type ADC. So we know it is the only one circuit which is using integrator. In all other circuits we were not looking to the usage of the integrator. So it is also named as an integrator type ADC. And if at all we are interested to identify what is the conversion time, if you look to the worst case is a case all the bits to be 1. For 3-bit case, but all we are looking, when we are reading all the bits are 1, it is the worst case. So we know to get all the bits are 1 after clearing this full cycle, after passing to this full cycle, it is to go again coming to all the bits are to be 1. It means for any digital readout, 8 clock pulses are must, later we are going to have for 3-bit case. Based on this, we are looking for n-bit case, for any digital readout to the power of n number of clock pulses are must, later only we are going to have the readout. So if you take the worst case, it is coming to be to the power of n plus to the power of n minus 1 into Tc. So it is the thing what we can estimate as the maximum conversion time. So you can look, this is nothing but to the power of n plus 1 minus 1 into Tc. N plus 1 minus 1 into Tc. So we can look here, comparing with any other analog to digital converter, this integrated type or dual slope analog to digital converter is having lengthy conversion time. It may be having a lengthy conversion time, but its conversion accuracy is good. Comparing with other analog to digital converters. What we are looking is, we are looking the point-to-point comparison between the analog signal and the reference voltage. So basically, because of this, the integrated type analog to digital converter comparing with other analog to digital converter is having better conversion accuracy, but it is having a problem of lengthy conversion time. It is a disadvantage. Having a lengthy conversion time is a disadvantage. And if at all we are looking to the advantages, we already mentioned, I am consolidating once again. Conversion principle is straightforward and the circuit complexity is less. Conversion principle is straightforward and we are looking the circuit complexity is less. Conversion accuracy is good. So these are the primary advantages of this dual slope analog to digital converter. So all these advantages we are looking at the cost of this lengthy conversion time. Now based on this, we can look now why we named the first circuit as a flash type. If at all we are looking, if you consolidate, successive approximation type ADC is having conversion time n into Tc. Counter type, for worst case to the power of n into Tc. For worst case we are talking. And dual slope, we are looking to the power of n plus 1. Of course, here also if you want to the power of n minus 1 into Tc, you only have to take as an exact. It is, as I said, worst case. If you come to this to the power of n plus 1 minus 1 into Tc for dual slope, it is for worst case. So the conversion time is in the increasing order. If you look to the comparator type, ideally speaking, if at all the comparators are having uniform propagation delay, what is the conversion time will be having an estimation? The conversion time is only in terms of the propagation delay. In the practical situation, if at all we are looking, we are having the usage of buffer circuit. Because of the usage of buffer circuit, of course, at the maximum we are having the usage of 1 clock. So comparing with any other analog to digital converter, the conversion time of this comparator type ADC is negligible, almost negligible, very small. The reason to name this as flash type ADC. And why we named this as comparator, I already mentioned, again I am repeating, it is a circuit where we are having the usage of multiple number of comparators, whereas in other circuits we are having no doubt usage of the comparator but only one comparator, but here we are having the usage of the multiple number of comparators. Hence it was named as a comparator type. And coming to this counter type analog to digital converter and dual slope analog to digital converter, even here also, whenever the size of the comparator is increased from n to n plus 1, the conversion time is coming to be double. Whereas in the case of this comparator type, whenever it is coming from n to n plus 1, we are looking the number of comparators are coming to be double. Number of comparators here double, whereas here number of here the conversion time is coming to be double. So these are the basic differences what we can look among these various analog to digital converters. Whatever the analog to digital converter circuit practically we are having the usage, it must be any one of this. So in most of the digital voltmeters, we are having the usage of the dual slope ADC. The reason is cost is less, conversion accuracy is good, and of course we can look the conversion time is more. Wherever the conversion time is not a critical, at all such places it is preferable to use. In the digital voltmeters, normally we are measuring by human being the measurement we are having. So conversion time is not a critical thing, so that most of the digital voltmeters they are having the usage of the dual slope analog to digital converter. Wherever we are not having the usage of the real time applications, it is preferable to use. For real time applications, of course, flash type may be better because the conversion time is very less, but cost will be more comparing with any other analog to digital converter. The cost is more because of more number of comparators usage, and of course proportionally the circuit complexity also will increase. So these are the things, these are the differences, these are the better things what we can look among these various analog to digital converters.